In this video, we're gonna present our experiment 6 from group 3, Thermodynamics, the torsion of bar. I'll introduce our group members, me, Henry, Iman, Diomon, and Kwong, and also Wang Teng. Let's start with the introduction. For the introduction, the torque is the force that causes an object to rotate about an axis. Analogous to how force causes linear acceleration, torque causes angular acceleration. There are two types of torque. The first one is the static torque, where it does not cause any angular acceleration. An object remains in equilibrium when torque is applied, while the another one is the dynamic torque, where it causes angular acceleration of the object. When a shaft or a rod with a circular cross-section is twisted, it rotates through an angle of twist theta. This angle depends on how much torque is applied, the length of the shaft, its radius, and the material's properties. And also for the modulus rigidity, G is the property of materials that measure how much it resists shearing twisting. A higher G means the material is stiffer in twist. While as for the polar moment of inertia, J is a geometric property that measures an object's resistance to twisting, just like how the moment of inertia resists bending or rotation. As for this experiment, it investigates how different materials such as aluminium and copper alloy respond to torsional loads by measuring parameters like the angle of twist, torsional shear stress, and also the shear modulus. The shape of the bar plays a critical role in its torsional behavior. In particular, hollow shafts often offer better strength to weight ratios than solid ones due to the higher polar moment of inertia that we are trying to investigate the one of the object, the hollow copper, by examining both material type and also the geometric form. This experiment aims to provide a comprehensive understanding on how structural properties affect torsional performance. As we are using one of the hollow materials, which is hollow copper, the key properties of hollow materials are actually lighter weight than solid materials, higher strength to weight ratio, better bending resistance, which is higher moment of inertia, better torsion resistance, higher polar moment of inertia, and also the material efficiency of the material bears the most of the stress. And there are a lot of application of that use torque, where cars, wind turbines, motors, and also bicycles. Moving on with the objectives, the objective that we have in this experiment is to investigate the relationship between the torque T and the angle of twist theta of the circular cross-section bar, and also to determine the modulus of rigidity G of the material. As for the scopes, we have four scopes. The first one is the experiment investigate the torsional behavior of three solid bars made of different types and also shapes of materials, which are aluminium, copper alloy, and also a hollow copper alloy. While the second one is the range of applied incremental torsional loading from 5 Newton to 40 Newton. And also the angle of twist is measured from a fixed clamp at 200 millimeter and 400 millimeter length. And also lastly, the angle of twist of a circular cross-section bar, the different angle.
For theory, torsion is the twisting of a shaft due to an applied torque. This torque causes an angular deformation called the angle of twist. The amount of twist depends on the shaft material, geometry, and the load applied. Torque: when a load is applied to a pulley system attached to a shaft, a force due to gravity acts on the shaft. This force applied at a perpendicular distance from the shaft center creates a torque given by the equation T equals to Fd, where F equals to mg is the weight of the load, d is the distance from the axis of the shaft. This torque introduces torsion in the shaft. Torsion: as a torque is applied, the shaft twists and develops an angular deformation known as the angle of twist, denoted by theta. The relationship is given by theta equals to TL over Jg, where T is the applied torque in Newton millimeter, L is the length of the shaft, J is the polar moment of inertia of the cross-section, Z is the modulus of rigidity or shear modulus of the material. Now, let's discuss the polar moment of inertia, J, which differs depending on whether the shaft is solid or hollow. For a solid circular shaft, J equals to pi over 32 d power of 4. For a hollow circular shaft, J equals to pi over 32 do power of 4 minus di power of 4, where d is diameter for a solid shaft and do is the outer diameter and di is the inner diameter for a hollow shaft. A solid shaft has material throughout, offering higher resistance to twisting, while a hollow shaft lacks central material and thus has less torsional strength. Modulus of rigidity. We can experimentally determine the modulus of rigidity G by measuring the angle of twist theta at different applied torques. Rearranging the torsion formula gives G equals to TL over J theta. Also, by plotting torque versus angle of twist, we get a linear relationship within the elastic range. The slope of this graph is m, and we can use it to compute G using G equals to L over Jm. This confirms that torque and angle of twist are directly proportional for materials behaving elastically. Here are some theoretical values for G used in experiments. Aluminium is 26 gigapascal, copper alloy is 45 gigapascal, hollow copper alloy is 45 gigapascal. Same as solid since G is a material property.
Okay, hello. So next, I'm gonna present about the experiment setup. Okay, so first we have the aluminum rod, load hanger, pulley, rotational scale and pointer, loads which is we use 5 Newton until 40 Newton, copper alloy rod, a ruler, copper alloy hollow rod, drill chuck key, digital caliper, and fixed end. So for the methodology, firstly with step 1, measure the radius of all three rods using digital caliper and record the inner and outer diameter of rods in table 1 to 3. The diameter of the pulley is measured using ruler to calculate the torque T and the polar moment of inertia J. So second step is secure the aluminium rod at one end in fixed clamp using the drill chuck key and the other end in pulley with the measurement of 200 millimeter to ensure it is held tightly to prevent any movement. For, for step 3, the rotational scale and pointer is set at 200 millimeter from the fixed end and the pointer is set to 0. This is to ensure the pointer is aligned with the 0 mark before applying any load to prevent parallax error. So step 4, repeat step 1 until 3 by applying loads from 5 Newton until 40 Newton to the pulley at the end of the rod. For step number 5, record and measure the angle of twist at each weight of increment for both rod lengths in table 1. Step 6, remove all the loads, change the rotational scale and pointer to 400 millimeter from the clamp and repeat step 3 until 5. Step 7 is repeat step 2 until 6 by replacing the aluminum rod with copper alloy and copper alloy hollow rod. Record it in table 2 and 3. For step 8, calculate the polar moment of inertia J for the solid rods, aluminum and copper alloy. Use the formula is stated there, where D is the diameter of the rod. For the hollow copper rod, use formula that for hollow rod, which is where the D is the outer diameter and D naught is the inner diameter. For step number 9, calculate the modulus of rigidity G. Use the torsion formula, which is G equal to TL over J phi, where T is the applied torque, Newton millimeter, L is the length of the rod, millimeter, theta or phi is the angle of twist in radians, J is the polar moment of inertia, millimeter, power of 4. So last but not least, we need to do the graphical analysis. Plot angle of twist theta against the torque for each rod, aluminum, solid copper and hollow copper on separate graph. And compare the experimental modulus of rigidity G with theoretical value for each material to assess accuracy.
So the next part is the result. So this is step 1. This is the data for aluminum solid bar. So the outer diameter is 6.55 millimeters and it is solid, so there's no inner diameter. So we can calculate the torque at 200 and 400 millimeter by multiply the weights of the rods. Then we can record our angle of twist. Then it can be converted to the radian. Next one is the table 2. This is the data for copper solid bar. So first we record our outer diameter, which is 5.94 millimeters. So similarly, we can calculate our torque at 200 and 400 millimeter. Then we record our angle of twist in degree, then be converted to radian. This is table 3 is the data for copper hollow bar. So the outer diameter is 5.97 millimeter and inner diameter is 3.06 millimeter. So torque at 200 and 400 is calculated. Then record the data for angle of twist in degree form, then be converted to radian.
Discussion. These are the graph we get from angle of twist in radian against torque in Newton millimeter. So this graph for solid aluminium. On the left hand side it is solid aluminium at 200 millimeter, and the right hand side it is at the 400 millimeter distance. As you can see, both of them in linear, and the slope for solid aluminium at 200 mm is 4.99 exponent negative 5, and for solid aluminium at 400 mm is 8.73 exponent negative 6. And these are the solid copper. On the left is the solid copper at 200 mm, and at the right is the solid copper at 400 mm. Also, both of them in linear. Slope for solid copper at 200 mm is 7.28 exponent negative 5, and slope for solid copper at 400 mm is 1.75 exponent negative 5. Lastly, these are the graph for hollow copper. On the left is the hollow copper at 200 mm with the slope 8.48 exponent negative 5, and on the right is hollow copper at 400 mm with the slope of 2.09 exponent negative 5. Let's take a look at this graph that show how different materials respond to torque. As torque is applied to each shaft, we see the angle of twist increases in a straight line. This tells us the relationship is linear, which means these materials are staying in their elastic range. Now, let's compare the materials. Solid aluminium twists the least for the same amount of torque. That means it is the stiffest, harder to twist. Solid copper twists a bit more, so it is less stiff than aluminium. And hollow copper twists the most, since it has less material to resist the torque. We also tested two different shaft lengths, 200 mm and 400 mm. Interestingly, the shorter shaft twists more for the same torque, so the longer the shaft, the more it resists twisting. So overall, both material and the length of the shaft play a big role in how it responds to torsion. Now, let's talk about what happens when we change the length of the bar. From the table, we can see that when we increase the length from 200 mm to 400 mm, the bar twists more under the same torque. This causes the slope of the torque versus angle of twist graph to decrease. So, longer bars are more flexible and less stiff in torsion. Next, let's compare the material based on how much they resist twisting. Solid aluminium has the highest resistance to twist. That is because it has the highest values of both J, polar moment of inertia, and G, modulus of rigidity. For solid copper is in the middle. It is not as stiff as aluminium but better than hollow copper. Hollow copper has the least resistance. It has lower values of J and G, so it twists more easily. This confirms that both material and geometry, like whether the shaft is solid or hollow, have a big impact on how it handles torsion. So, in real-world application, if you need something strong and twist-resistant, solid shaft made of stiffer materials like aluminium are the better choice. This is the example calculation on how we get J and G for aluminum solid bar, copper hollow bar for both distance at 400 mm and 200 mm. Comparison between theoretical and experimental values of modulus of rigidity G. The theoretical modulus of rigidity is about 26,000 Newton per millimeter square for aluminium and 45,000 Newton per millimeter square for copper. In our experiment, the 200 millimeter aluminium bar gave a G value of 22,936.71 Newton per mm square, which is close to the theoretical value. But the 400 mm aluminium bar show a much higher G value of 259,949.37 Newton per mm square, which is likely due to mistake in units or an error in calculating the slope. For solid copper, the 200 mm bar gave a much lower G value of 22463.25 Newton per mm square, while the 400 mm bar gave a much higher G value of 187,515.4 Newton per mm square. This result suggests there might have been material defects or error in finding the slope of the torque angle graph. Hollow copper show a similar pattern with better result from the 200 mm bar and more errors in 400 mm bar data. Overall, the 200 mm bars gave more accurate result, while the 400 mm bars had bigger errors. The difference between experimental and theoretical G value is often caused by measurement errors, incorrect unit conversions, mistake in slope calculation, equipment issues like loose clamps, or defect in materials. Theoretical values are based on perfect conditions which are hard to achieve in real experiments. Being careful with setup and checking data closely can help reduce this error. To what extent does the experiment verify the torque or twist formula based on the graph plotted? The theoretical relationship for the angle of twist is theta equals to TL over GG. When plotting angle of twist theta against torque T, the equation takes the form of y equals to mx plus c, where theta is y, t is x, and the slope m equals to L over Jg. This confirms that the graph should be linear, consistent with theory. From the graph, we can see a clear linear trend which supports the theoretical model. However, the slope and y-intercept aren't a perfect match. This is mostly due to experimental factors like difference in shaft length 200 mm versus 400 mm and shaft diameter, which affect the slope and cause some mismatch between the experimental and theoretical result. Conclusion: overall, this experiment successfully confirms the torque versus twist formula in a qualitative way. All the graphs show that torque increases linearly with the angle of twist, just as theory predicts. Although we notice some numerical difference, they are likely caused by things like shaft length difference, diameter variations, and small experimental errors. These differences are minor and don't change the overall conclusion. So we can say that the experiment effectively verifies the theoretical model, especially the idea that torque and angle of twist are directly proportional, even if there are small differences in exact values due to real-world conditions.
So for discussion two is the comparison between the three different types of bar with different lengths of rotation scale, and also the pointer from the fixed clamp. So from our comparison, the comparison between solid aluminum, solid copper, and hollow copper bars shows that the solid aluminum twists the least, suggesting that the highest torsional rigidity in the experiment. This may seem unexpected, as the copper usually initially has the higher shear modulus, which is around 44 GPa, than aluminium, which is 26 GPa, where meaning it should be materially stiffer, but based on our result, it's the other way around. However, the slightly larger diameter of the aluminum bar, 6.51 millimeter versus the 5.94 millimeter for copper, significantly increases its resistance to twisting, and as torsional stiffness is highly sensitive to diameter, which is directly proportional to the radius power 4. So this might be the one of the reasons that affected logical or theoretical result. Additionally, the difference in clamping, bar alignment, or also the measuring position could also have influenced the result. Despite copper's inherent material stiffness, these factors led to the greater twist observed in the solid copper ball, which explain our results. Overall, aluminum appears stiffer due to the geometric and setup related advantages, while hollow copper with reduced material show the highest deformation.
Okay, for the discussion number three, which is based on our finding, explain the relationship between the modulus of rigidity of materials with the parameters such as type of material for the bar, length of the bar, the shape of the bar, and polar moment of inertia. So, the of rigidity G is a material property that describes that it's resistant to shear deformation. The provided data allow us to analyze how G relates to the type of material, bar length, bar shape, and polar moment of inertia G. Okay, first for the criteria is the type of material. Solid aluminium, higher G values compared to copper, indicating aluminium is more rigid under shear for the same dimensions. And for the solid copper, lower G values than aluminium, showing copper is less rigid. And hollow copper, even lower G values than solid copper, as hollow structure generally reduce rigidity. So the number two is the length of the bar. For all materials, G increases significantly with bar length. And this is because longer bars exhibit less angular twist for the same torque, leading to higher calculated G values. Okay, next for number three, shape of the bar. Solid versus hollow. Hollow bars, example, hollow copper, have lower G compared to solid bars of the same material, which is copper. As hollow section reduce the effective shear resistance area, the hollow copper's J is slightly less than solid copper's J, contributing to lower rigidity. Number four, polar moment of inertia J. J quantities the bus resistant to torsion. Okay. J quantifies the bus resistant to torsion. Higher J correlates with higher rigidity G as more material is distributed farther from the axis, resisting twist better. Conversely, lower J results in lower G. So, the modulus of rigidity depends on material properties, which is aluminium versus copper, bar geometry, solid versus hollow, and length. Polar moment of inertia J is critical as it integrates these geometric factors into torsional resistance. Longer bars and solid section enhance rigidity, while hollow section reduce it.
Okay, so in conclusion, this experiment was conducted to investigate the torsional properties of three types of cylindrical rods, which are the solid aluminium, solid copper, and hollow copper. So the primary objective was to analyze the relationship between the applied torque and the resulting angle of twist, and to determine the modulus of rigidity for each material. So a consistent linear relationship between the torque and the angle of twist was observed above 200 millimeter and 400 millimeter lengths. So confirming the material behave elastically within the limit tested and aligning with theoretical expectation based on the Hooke's law for torsion. So among the specimen, the expectation among the specimen, the solid aluminium rod demonstrated the highest shear modulus, this indicating that superior rigidity and resistance to torsional deformation. Solid copper exhibited moderate rigidity, while the hollow copper showed the lowest G values, highlighting the effect of reduced cross-sectional area on torsional strength. So from the experiment, the calculated value for the modulus of rigidity G was as follows. So for solid aluminium, we can see the average is 141,443 Newton per millimeter square. For solid copper is 104,989 Newton per millimeter square, and for hollow copper is 92,240
Newton per millimeter square. So this result affirms that the modulus of rigidity increases with the material thickness. So a higher G value indicates that a more rigid material that resists the shear deformation as seen in aluminium. Conversely, a lower G value as observed in hollow copper suggests the material is more flexible and deform more easily under the shear stress. Although the experiment provided meaningful insight, certain discrepancy were noted between the value obtained at different lengths. So this inconsistency may be attributed to the experimental limitations such as the manual angle measurement, uneven torque application, or dimension inaccuracy, especially in measuring the inner diameter of the hollow rod, which directly affect the calculated polar moment of inertia J. So, in order to improve the precision and reliability of future experiments, the following enhancements are recommended. So, the first is use digital angle sensor or encoder for more accurate twist angle measurement. Second is employ a calibrated automated torque application system to maintain the consistent loading. The third is perform the experiment in a temperature controlled environment to reduce the variability in material behavior and conduct the multiple trials for each sample to allow the statistical validation. And the last one is utilize high precision measurement tools, particularly for determining diameter in hollow specimen. In conclusion, this experiment successfully demonstrated the influence of material composition and geometry on torsional performance. The findings reinforce the importance of selecting appropriate material based on their mechanical properties in engineering application where the torque resistance is critical. So for safety procedure, the first one is wear the closed toe shoes to protect feet in case of drop tools or equipment. And the second is check the bar for cracks or defect before the experiment. A faulty bar may break under the top. The third is use appropriate torque limit based on material specification to avoid exceeding yield strength unless intention for testing failure. And the fourth is stand clear of the bar rotational plane to avoid injury if the bar snap. Monitor the angle of twist readings to anticipate the potential failure and ensure that your eyes are positioned perpendicular to the scale to avoid the parallax error. And ensure the diameter along the root is uniform to prevent inaccurate result due to uneven stress distribution, and ensure that each solid root is clamped securely before applying any loads. Because a poorly clamped root can slip or eject under torsion, causing potential injuries or damage to the apparatus. Add or remove the weight slowly and carefully to avoid sudden jerks that can cause imbalance of injury. And the last one is use the digital caliper carefully, keep fingers away from the jaws and check the calibration to ensure no zero error to ensure the accurate readings and avoid the damage. So these are some reference that we use indeed experiment 6 which are torsion of the bar. So overall, this is our presentation for report 6. Thank you, Doctor.